This is section 4.1. This is the first part. This section is broken up into two parts, and we're talking about polynomial functions, graphing polynomial functions, ideas about polynomial functions, and a little bit of a little example about a model that involves a polynomial function. All right, so let's talk about, first of all, what is a polynomial? Well, it's a function. We're going to call it p of x. Sorry about the blurriness here. I know it's a little pixelated. But what we have is, so you have p of x. It's a function, so it passes the vertical line test. This function has what are called terms. In this particular case, you have n terms. So actually n plus 1 terms in this particular case. You have 1, 2, all the way to the n plus 1 term. So it's this little part that has a n. This little n down here is called a subscript. So that little a sub n represents a real number, and then you have the variable x, and then you have x raised to some exponent n. Yeah. Right now this polynomial here, or this theoretic polynomial, is in descending order. So the idea here is the highest exponent of n is at it's the leftmost term. And then the exponent of n starts decreasing until it just becomes 1 over here, and then eventually becomes 0. So the a's of n, so the a with the little subscripts, those are real numbers. They're called coefficients. And so in this particular case, we have n plus 1 terms. This would be 1, so this would be the leading term, the next term, then the next one, and so on all the way until you get to this term over here that has no x's. This term is called the constant term. All right, so yeah, the terms are separated by addition or subtraction. So this could be plus, this could be minus. It just depends on the sign of the a sub n. The degree of the polynomial. The degree of the polynomial is the highest exponent of n. And if your polynomial is not arranged in descending order, then it might be a good idea for you to write it in descending order for the purposes of identifying the degree and also maybe for factoring purposes. So, okay. So a sub n x to the n, that's called the leading term. The leading term. And the leading term tells us a lot of information about the graph of the polynomial. We'll see that in a second. The a sub n, so this real number a sub n, is called the leading coefficient. And a sub 0 is the constant term or constant coefficient. The domain of every polynomial function, so if you're dealing with a polynomial, the domain is going to be from negative infinity to positive infinity. What that means about a polynomial is that they're nicely behaved. They do not have gaps, there's no holes in the graph, there's no crazy behavior. They're pretty smooth graphs that go from negative infinity to positive infinity on the x-axis. Okay, so let's get into our first example. Let's just see if we can recognize a polynomial. So in the first exercise, we are given 3 little functions, parts A, B, and C, and what you have to determine is which one is a polynomial, which one is not a polynomial. Okay, so pause the video, see if you can determine which ones are polynomials, which ones are not. Alright, so hopefully you've paused this video and you know which ones are polynomials and which ones are not. So I would say that this guy right here is definitely polynomial, part A. It's definitely polynomial. Part B, I mean, it's 2 divided by x plus 5. Technically, I guess I could write this as 2 times x to the negative 1, because a negative exponent corresponds to division. Let me just kind of remind you up here. I mean, not that you need to know this for this video, but just x to the negative 1 means 1 over x. X to the negative 2, I guess, means 1 over x squared, and etc., etc., etc. Well, a polynomial should not have negative exponents. And so right now, technically, I'm dealing with a negative exponent or a division, so this is not a polynomial. So this is not polynomial. Okay, what about the last one? Is it a polynomial or is it not? This one's definitely not a polynomial. This is definitely not a polynomial. Why is it called polynomial? Well, because, well, what does the word polynomial mean? So poly means many, and I guess polynomial means term. So it's some function that has all of these many terms. But remember that the exponents should be positive whole numbers. Positive whole numbers. So you don't want fraction exponents, you don't want negative exponents. Those are not polynomials. Okay. It's gonna be to our advantage once, so our primary goal is going to be graphing polynomials. And in order to graph polynomials, it's definitely going to be useful to have to factor them. And why do we want to factor them? So that we can see where they hit the x-axis, where they intersect the x-axis. Okay, factoring polynomials is not an easy task. There's some work involved in trying to factor polynomials. You might have to do some long division, some synthetic division. You might have to do some testing using your calculator to find the factor form of a polynomial. In this other next example here, they give us a third-degree polynomial. So this is a polynomial of third degree. It has 4 terms, 1 term, 2, 3, 4 terms. The leading coefficient right now is a 1, even though I don't see any number in front of my x cubed term. Technically there's a 1 right there. So my leading coefficient is 1, my constant coefficient is -6. And they just told us that somehow, by some magic, some mathematical wizardry, they were able to factor this third-degree polynomial. To be factored just means that you were able to express it as a multiplication. So they were able to express it as this multiplication, x plus 3 times x plus 1 times x minus 2. And now they're asking us, what are the linear factors of h of x? Okay, well, the linear factors are going to be just, x plus 3, x plus 1, and x minus 2. So here we're going to conclude that the linear factors are these simple little binomials, x plus 3, x plus 1, and x minus 2. Yeah. And by the way, these little things are called binomials. Bi means 2. You have 2 terms. So it's kind of like polynomial. I guess like if I had a polynomial with 3 terms, that would be called a trinomial. If I had a polynomial with 4 terms, that would be a quadrinomial, quintinomial, etc., etc. Okay. The next one. Let's try the next example. In the next example, I am being asked, what are the linear factors of this second-degree polynomial? And maybe the question here is not as obvious because they didn't give me the factor form of my polynomial as they did in the previous example. In the previous example, they gave me the factor form over here. So pause the video, take a second, factor this polynomial, and then tell me what are the linear terms. Okay, so factoring is going to be quite the skill to have available right now for this section. So let's see. I am going to try to factor this by some trial and error. So x, I'm thinking, goes there, and x goes there, so that I get the term x squared. And now, can you think of some couple of numbers that multiply to positive 12? So these two numbers multiply to positive 12 and add up to -7. And I'm thinking -3 times -4. -3 times -4 is, if you multiply those, that's -12. And if you add -3 plus -4, that's -7. All right, so -3, -4, and I think that's our that's the factor form of this polynomial. And so then the linear factors, I guess, are linear factors are just x minus 3 and x minus 4. comma I should say, comma x minus 4. Okay, good. So again, this why do we want to factor polynomials? Well, because eventually we're going to want to find the x-intercepts. And to find the x-intercepts, we're going to have to set the whole the y equal to 0. And that's when factoring will come in handy. Okay, let's talk about what's called the leading term test. So leading term test. And remember, if you have a polynomial p of x, a n x to the n plus etc a1x plus a0, this is called well, actually let me what I should say, this whole thing right here, this is my leading term. Okay, so just based on the leading term, you can get a lot of graphical information about your polynomial. So just by looking at the leading term, and again, I guess it helps to have the polynomial written in descending order. So from highest exponent on the left to lowest exponent on the right. If you have it in that format, it's easy to identify the leading term, and then you can tell a lot of information about the graph of the polynomial. All right, so let's look at some examples of leading terms and different polynomials here. So this one's hard to see, I know, but this little function here, it's x squared. So x squared. And x squared looks like a little parabola that opens upward. Yeah, that's a polynomial of degree 2. It only has one term. Okay, now let me look at next. So I mean, I guess first of all, I should have said, let's look at even degree polynomials. So polynomials with even degree. That means that the highest exponent is an even number. So x squared. Here I have negative x to the fourth. Negative x to the fourth. That's the leading term. Negative x to the fourth. And this looks kind of like an upside down little u. Now I have x to the sixth. 1/2 x to the sixth. It still looks like a u, but that opens upward. And then I have this polynomial here at the right here. I mean, here technically, I guess in order to just kind of make it a little bit more obvious, I could have written it like this. Negative x to the 10th minus x plus 1. So now it's in descending order. And well, it's even degree. Why? Because the exponent is even. I have a negative leading coefficient. And my polynomial looks like an upside down u. So it looks to me that if I'm dealing with an even degree polynomial, the graphs tend to look like either an upside upside down u or a right side up u. I guess it depends on what's called the leading coefficient. If the number in front of your x, the number in front of the variable x is negative, then it's going to be upside down. If the number in front of your x is positive, you're going to be, I guess, regular, right side up. All right, let's look at some polynomials of odd degree. So now the degree is odd. The degree is going to be something like 3, 5, 7, 9. Okay, let's see. So here I have x cubed, x to the third. And we have this little graph. Starts at the bottom left, goes up towards the top right. Okay. Now the next odd degree polynomial that I have is this negative x to the fifth. This is negative x to the fifth. Again, I'm sorry about these notes. They're a little difficult to see the small print. So this says negative x to the 5. And if you notice, it's similar to x to the 3. It's just that the orientation is different. With x to the 3, the number in front of x to the 3 was a 1. Even though I don't see any 1 there, but technically there's a 1 there. It's just 1 times x to the 3 is just x to the 3. And we went from bottom left to upper right. Now in the next little graph here, we have negative x to the 5. And well, that means now that my coefficient is a negative 1, and I'm starting from upper left to bottom right. Yeah. Now I have negative x to the 7th. Negative x to the 7th is going to be similar to the previous one, negative x to the 5, in that it starts in the upper left and goes to the bottom right. And then I have 1/2. Now it's positive, so the number in front of my x is positive now. 1/2 x to the 9th. And I guess that's similar to the first one, x to the 3rd. So from the bottom left to the upper right. Yeah? So hopefully you see the pattern that's happening here. And that's what this next little box is going to tell us. So just by looking at the leading term, first of all, if n is even, our graph looks either like a U or an upside down U. If it's odd, we have this little lower left to upper right or upper left to bottom right behavior. Depends on the sign of the leading coefficient. So yeah, this is the leading term test. So if I look at the leading term, then the behavior of the graph as x goes to positive infinity or x goes to negative infinity can be described by one of these 4 little patterns. So again, if n is even and the leading coefficient is positive, I have an upside down, like just a little u. And these little like zigzaggy lines in the middle means that my graph could do all sorts of crazy behavior in the middle. I don't know what happens in the middle, but in the long term, as x goes to positive infinity, that means as x goes to the right, my graph goes up, and as x goes to negative infinity, my graph goes also up. So that's if the degree is even and the leading coefficient is positive. If the degree is even and the leading coefficient is negative, so less than 0, then I have an upside down u. If the degree of my polynomial is odd and I have a positive leading coefficient, I have this little behavior, bottom left to upper right. If the degree of my polynomial is odd and I have a negative leading coefficient, then I have this behavior of upper left to bottom right. Okay, and again, here in the middle, we don't know anything about the polynomial. In the middle, it's a wild world. Who knows what happens in the middle? But at least we know the end behavior. We know the end behavior of our polynomial just based on the leading coefficient. Or sorry, the leading term. All right, so then what we're going to say, so let's complete this next little table here. So assume that you're dealing with an even degree polynomial and that the leading coefficient is positive. So if I'm dealing with an even degree polynomial and the leading coefficient is positive, as x goes to negative infinity, what happens with my y values? Remember, f of x just means y. So as x goes to negative infinity, so if my x's go to forever to the left, it looks like my y values are going up. Because I mean, my degree right now is even and the leading coefficient is positive. So my graph should look like a U. So as x goes towards negative infinity, y also goes to, well, y goes to positive infinity. And as x goes to positive infinity, so now if my x goes to the right, my y's also go to positive infinity. Yeah? So pause the video, complete this, the other 3 little scenarios here, and see if we get the same ideas. Alright, so the next thing, if my polynomial has even degree and it has a negative leading coefficient, so even degree and negative leading coefficient, then as x goes to negative infinity, so even degree and negative coefficient means an upside down u. So as x goes towards positive infinity, my y's are also going towards negative infinity. And as x goes towards positive infinity, well, since it's an upside down u, my y's are also going to negative infinity. Okay, the next one. So now I'm dealing with an odd degree polynomial. So odd degree polynomial with positive leading coefficient. So as x goes towards negative infinity, so right now I'm dealing with this scenario right here. So I have an odd degree polynomial, positive leading coefficient. So as my x's go towards negative infinity, as my x's go to the left, what happens to my y's? Well, they seem to be going down. So I'm going to say negative infinity. And as x goes towards positive infinity, so as my x's go to the right, what happens with my y values? It seems like they're also going up. So I'm going to say to positive infinity. And the last one, so now I'm dealing with an odd degree polynomial with a negative leading coefficient. So odd degree polynomial, negative leading coefficient, this is what the long-term behavior looks like. So as x's go to the left, what happens with my y values? I would say they go up, so they go towards positive infinity. And as my x's go to the right, what happens with my y values? It looks like they're going down. So I'm going to say negative infinity. Yeah. And by the way, this idea is here of as x goes to positive infinity, negative infinity, this type of, I guess, symbolism will definitely come in handy once you get into Calc 1, when you start talking about the limit as x goes to positive infinity, the limit as x goes to negative infinity. So keep this idea in mind. You might end up using it later on a lot. All right, let's move on. Let's determine some things about some polynomials. So we have a lot of examples here of polynomials. I guess I have 5 polynomials. This is a polynomial, that's a polynomial, this is a polynomial, this is a polynomial, that's a polynomial. So I have 5 polynomials, and they're going to ask me to determine some things about these polynomials. So pause the video and see if you can answer here. What's the degree? What's the leading term? What's the leading coefficient? And sketch a little graph of each of these polynomials. All right, so hopefully you have completed this little table, and I feel pretty comfortable about the graphical information that you know about, just from looking at the leading term. So our first, the top one here, f of x equals 3. That's called a constant polynomial. Notice that there's no x's involved here. So what's the degree then? Because we said that the degree is supposed to be the highest exponent of x. So I don't even see any x here. So then what is the degree here? Turns out that the degree here is 0. Why? Because turns out that, I guess you could think of this as being 1 times 3. Yeah? Well, 1 times 3 is just 3. And turns out that 1 is the same thing as x raised to the 0. Anything raised to the 0 is 1. So x to the 0 turns out to be 1. I guess we're taking advantage of this little fact about exponents. Anything raised to the 0 power turns out to be 1. So technically there is an x here. It's just that it's x to the 0 power. Yeah? And so then the degree of this polynomial is 0. What's the leading term? What's the leading term? Well, I guess we could just say the leading term is, if you wanted to be very, kind of detailed here, you would say that the leading term is 3x to the 0. Well, that's just the same thing as just 3. It's the same thing. Yeah. What's the leading coefficient? Well, the leading coefficient turns out is just the constant, the number in front of my x. We said that in this case it's x to the 0. So the leading coefficient here, it turns out to just be 0. I'm sorry, 3. It's 3. Okay, and what does the graph of this thing look like? What does the graph of this polynomial look like? So is 0 even? Is 0 odd? I mean, this is a weird polynomial. Our whole talk about even and odd degree polynomials that we just had a second ago kind of fails for this one, because 0 is neither even nor is it odd. So right now think about just the function y equals 3. That is a horizontal line. So y equals 3 looks like this. So that's my x-axis, this is my y-axis, and if that's 3 right there, then f of x equals 3 is just, this is f of x equals 3. It's just a horizontal line. A horizontal line that hits the y-axis at 3. That's what the graph looks like. Alright, so keep that in mind. So this is the simplest type of polynomial. It's called a constant polynomial. Constant polynomial, that means that it's a polynomial of degree 0, because x to the 0 turns out to be 1. Oops. We don't need to see that. All right, next. Now we have what's called a linear polynomial. So this is a polynomial of degree 1. I guess technically here we could say it's 2x to the first power minus 1. So this is degree 1. The leading term is, well, 2x. The leading coefficient is 2. And let's try to sketch a little graph of this. Okay, so this has a y-intercept of -1. So y-intercept of -1. Let's say -1 is down here. Oops. Let's diminish the thickness there. All right, so -1, and it has a slope of 2. So up 2 and over 1. I don't know, it's some little line that looks sort of like that. So this is f of x equals 2x minus 1. That's not the best sketch, but you get the idea. All right, next one. This is a second degree polynomial, because I see that the exponent here is 2. So 2. The leading term, I guess, is 4x squared. The leading coefficient is 4. And this is going to be kind of an ugly little sketch here. This is going to be an ugly little sketch. I know that right now from the leading term, I know that it's an even degree polynomial. It has a positive leading coefficient, so it's a little parabola that opens upward. So I don't know, I'm not really going to sketch it out with too much detail. I'm just going to say that it's a parabola that looks like that. Yeah. F of x. Again, if I wanted to be more careful, I would probably have to factor this polynomial so that I know where its x-intercepts are, and then that would give me a better sketch of the graph. And we will be doing that. But for now, we just need to give a little rough sketch, just to get the idea here. All right, the next one. So we had a constant polynomial, a linear polynomial, a quadratic polynomial. That means that it's of degree 2. Now I have a cubic polynomial of degree 3. Okay, so this is the degree is 3. The leading term is, I guess, x cubed. The leading coefficient turns out to be 1. That's the number that's in front of x cubed right there. And I would have to factor this in order to get a detailed sketch. And I'm not going to do that. But just what I know from looking at the leading term, 1x cubed, is that, well, the graph is supposed to do something like this. And then who knows what happens here. I'm going to put some like little ellipses, because who knows what happens in the middle, and then it goes upwards like that. So that is my polynomial f of x. Okay, the last one, I have negative x to the 4th. So that's this is called a quartic polynomial, degree 4, quartic polynomial. All right, so the degree here is 4. The leading term is negative x to the 4th, and the leading coefficient, the number of that's in front of my x in the leading term, well, turns out it's -1. Okay, so what I know from our previous talk is that if I am dealing with an even degree polynomial, so this is an even degree polynomial with a negative leading coefficient, its graph is going to look like an upside down U. All right, so I think the graph is going to end up looking something like this. I don't know what happens in the middle here, so I'm just gonna, that's why I put these little dots, because I don't really know the details of what happens in the middle of my graph. But I know that it's supposed to look like an upside down U. All right, so that is probably that's a very ugly sketch of my polynomial, but you know, we get the idea. We just want to know what happens in the long run here. All right, so the moral of this story so far is that just by looking at the leading term, you can get out already a lot of information about the graph of your polynomial. All right, so we're gonna need that. We're gonna need that here soon enough because we're gonna start graphing these things with more detail. All right, next example. So we are going to use the leading term test to determine the end behavior of each function. The end behavior means we're going to have to answer these questions. As x goes to positive infinity, what happens to my f of x? As x goes towards negative infinity, what happens to my y's? And remember, f of x and y are kind of synonymous. And then we're going to have to make a quick little sketch of the thing. All right, so pause the video and answer these 4 questions about end behavior of polynomials and try to get some little sketches of these graphs. All right, good. So hopefully you've gotten a couple of sketches here and you have determined the end behavior. Let's compare answers. So let me look at the first one, part A. I am dealing with even degree polynomial. Degree is 4, positive leading coefficient. So I know that the graph of this polynomial looks like a U that opens upward. So as x goes to positive infinity, as x goes to the right, my y's are going to go up. And as x goes towards negative infinity, so as my x's go towards the left, my y's are also going to go up. And this is going to be the most horrible little sketch you'll see ever, but it captures the long-term behavior. I guess it's just, it goes up this way. I don't know what happens in the middle, that's why I put these little dots, and it goes up that way. Yeah, I think that is the long-term behavior of my graph. All right, next example, part B. This is an odd degree polynomial. So this is odd degree, the degree is 5. I have a positive leading coefficient. So that means, actually I'm gonna sketch the little sketch of my graph first, and then I'll answer the thing about end behavior second. So I think my end behavior, or my polynomial, the graph of my polynomial should behave something like this. Yeah, and so based on that little sketch, I'm gonna say that as x goes to positive infinity, so as my x's go to the right, my y's go up, so they go towards positive infinity. And as x goes to negative infinity, so as my x's go to the left, my y's go down, so my y values go towards negative infinity. I think that's what's going on here. Next one. The next one. Here for this part C, be careful. Right now my polynomial is not written in descending order, and that's okay. I mean, you don't have to write it in descending order. All you have to do is determine what's the leading term. And right now the leading term is negative x to the third. Negative x to the third. I'm gonna write it in descending order just because I don't know, it just makes it a little bit maybe more obvious. Negative x to the third plus 5x plus 8. Okay, so right now I'm dealing with an odd degree polynomial. So it's odd degree, the degree is 3, and it has a negative leading coefficient. So negative leading coefficient. And so let me first sketch a little rough idea of what the end behavior looks like. I think right now we're dealing with this. So this is what happens if you have an odd degree polynomial with a negative leading coefficient. Okay, so then let's answer the questions about end behavior. So as x goes to positive infinity, what happens with my y values? So I think as x goes to the right, my y values go down. So I'm going to say f of x goes towards negative infinity. And as x's go towards negative infinity, what happens with my y values? So as my x's go to the left, so as my x's go left, my y values seem to be going up. All right, so I think that is what I can conclude from that polynomial. The last one. Um, the leading term is negative 3x to the 8th, and from that I know that the degree of my polynomial is even. The degree is 8. The leading coefficient is negative 3. So my graph should look like an upside down U. And so then as x goes to the right towards positive infinity, my y's go down, so towards negative infinity. And as x goes to negative infinity, so as my x's go to the left, my y's also just go down. Yeah? Alright, so again, the moral here is that just based on the leading term, you get a lot of information about the behavior of the graph of your polynomial. Again, but you see, we do not know what happens in the middle quite yet now, because you know, my graph could wiggle up and down a lot in the middle. Who knows? Now we need to kind of start thinking about what happens here, not just in the end behavior, but in the middle of my graph. And in order to determine what happens in the middle of my graph, we are definitely going to have to think about factoring polynomials or finding x-intercepts. Alright, so that's what the next thing's about. We need to find the zeros of polynomial functions. And zeros, well, they're just x-intercepts, or sometimes they're also called roots or solutions. Alright, so let's find some x-intercepts. Yeah, and in order to find the x-intercepts, we need to set the polynomial equal to 0 and solve. And so then let me remind you something that we talked about in the past. It's called the zero product property. Let me just kind of remind you about this. We talked about this some videos ago, and it says the following, that if A times B is equal to 0, then either A is equal to 0, B is equal to 0, or both. Or both. And so then how does this help us find x-intercepts? Well, look, right now what we have is a trinomial, 3 terms. If I'm able to express that trinomial as a multiplication, as something times something, and then I set it equal to 0, then I can set the factors equal to 0. So this zero product property is useful in finding x-intercepts. So our goal is to be able to express the polynomial as a product and set it equal to 0. Yeah, that's why we're setting things equal to 0, because we're using the zero product property to help us find x-intercepts. Alright, so let's find the x-intercepts of this first example. So I'm going to say 0 equals x squared minus 2x minus 8. And now I would like to rewrite this trinomial as a product so that I can take advantage of the zero product property. Okay, so that means factor. So I want to express this 3 terms as a multiplication of what are called binomials. Okay, so definitely I think I'm going to have an x here and an x there. And then I'm going to think some 2 numbers multiply to give me negative 8. So there are 2 numbers out there that multiply to give me negative 8. But when you add them, the sum is negative 2. And I think those 2 numbers are negative 4 and positive 2. So minus 4 and plus 2. Yeah, and now I'm going to take advantage of the zero product property, because now what I have is a product of 2 things that's equal to 0. Well, the only way that that can happen is if either of these factors, these are called factors, remember we said that these are called the linear factors, so I need to set the linear factors equal to 0. So x minus 4 equals 0, and x plus 2 equals 0, which says that this is x equals 4 and x equals negative 2. Okay, and so now I think I'm going to try to sketch a little graph of this. So now what happens here, let me look at the leading coefficient here. Or sorry, the leading term. The leading term is x squared. That means that I'm dealing with an even degree polynomial. It has a positive leading coefficient. Now I know where the x-intercepts are. So the x-intercepts are at -2 and at +4. Okay, and I have a little parabola or a little u that opens upward through these 2 points. Let's see, I think the midpoint is somewhere down here. And I guess this would be -8. So right now what I'm doing is I am trying to figure out, okay, if my, well, I don't know, let's see, if my x happens to be, so I found the x-intercepts. These are called the x-intercepts. Another thing that I could do is find the y-intercepts, just to be even more careful. To find the y-intercepts, you set your x equal to 0. And if I set my x equal to 0, well, then I have this y-intercept, 0, -8. Because if this is 0 and that's 0, well, then I end up with just -8. So my graph hits the y-axis at -8. That would be down here somewhere. Alright, so I'm going to just try to kind of join these 3 points together the best way I can. And again, sorry, my lines are a little wobbly here. Don't judge me too bad. There we go. So I think this is a little sketch of my polynomial g of x. It's an ugly little sketch, but you know, it captures the idea of the polynomial. Alright, you try the next example. The next example is a little bit harder. Because now you're dealing with a 3rd degree polynomial and you're going to have to factor it. And they definitely tell us here to use our calculator. Use our calculator to find the solutions. So see if you can tackle it yourself first. See if you can use the calculator here on your own to figure it out. And then let's compare answers. Alright, so hopefully you have you found the x-intercepts of this 3rd degree polynomial. So it's an odd polynomial. And you got a little sketch. Let's compare answers. Alright, so let me write my polynomial. So I have h of x is equal to x to the 3rd plus 2x squared minus 5x minus 6. And I mean, I sort of know just from the leading term test. So right now I have an odd degree polynomial with a positive leading coefficient. So I know that the graph is going to look in the long-term behavior of my graph is going to look something like this. Yeah, that is kind of what I expect my graph to look in the long term. But right now I'm also interested in the middle part, this little place where I put dots. I want to see what happens. I want to know what happens there. And so then what's going to have to happen here is that I'm going to have to find the x-intercepts of this 3rd degree polynomial. And they told us to use our calculator here. So let me bring out my calculator and think about this. There we go. Alright, let's see. I don't need double calculator, I just need one. So let me clear this. I am going to go to my graphing utility, first of all. Let me move my calculator a little bit up. There we go. So you can see all the buttons. So I'm going to go to y equals. And right now what I'm going to enter is the 3rd degree polynomial that was given to me. Let me just clear these other functions that I had in here before. So let me clear them. Okay, so let me enter my 3rd degree polynomial. So x raised to the 3rd. Alright, and then right now notice that my cursor is up here in the exponent. If you just keep on typing things, I'm gonna stay in the exponent. I don't want that. So I need to get down from the exponent. In order to get down from the exponent, you hit your cursor here. So I'm down now. And then plus 2x to the 2nd. Okay, let me get down from the exponent. Minus 5x minus 6. All right, so that's my polynomial. I'm gonna go to its graph. I'm gonna just hit graph right now. Actually, I'm gonna hit enter just so that the calculator registers the polynomial. Then I'm gonna go to graph. All right, so that is my polynomial right there. I mean, it makes sense to me. I know that the leading term will tell me that, I mean, we had this idea for long-term behavior, and that is kind of what's going on. It goes from bottom left to upper right. And right now what we're interested in is in figuring out where it hits the x-axis. So it looks like my polynomial hits the x-axis in 3 places according to my calculator. I'm going to use my calculator to find those points of intersection. How do I do that? I'm going to hit I'm gonna take advantage. There's this little thing in blue up here in my calculator that says calc, C-A-L-C. I want to access that, so I'm gonna hit second calc. And right now what we want is 0. Zeros are the x-intercepts. So let me go to 0, hit enter, and let me find the leftmost 0. Notice that there's this little blinking little dot on my graph. And I can control that little blinking dot. I can control its position by using my little cursors. Yeah. So right now my calculator wants me to give. So I wanna sort of approximate the x-intercept. It wants a left bound. Notice that it's asking for a left bound. So I'm going to go a little bit. So I think that's where my x-intercept is. But I'm gonna go just a little bit to the left of it. Just a little bit to the left of it, right there. And then I'm gonna hit enter. And now it wants a right bound. So the calculator needs a left bound and a right bound around the x-intercept to be able to compute it. So I picked a left bound. Now let me pick a right bound. I think that's a good right bound right there. I mean, I could even go a little bit higher. Let me go a little bit higher. I'm gonna enter. So you see, I have bounded my x-intercept. Now the calculator is going to use the left bound and the right bound to be able to find the x-intercept. Your calculator has a little built-in algorithm that is able to perform this. So let me hit enter. And according to the little calculations that my calculator just did, this x-intercept is -3. All right, so let me write that down. So I guess I'm gonna have -3, 0. That's an x-intercept. Let me find another x-intercept. So let me go to second calc again. Again, we said that we will want to go to 0, hit enter there. And now again, same situation. Now I want to find the next x-intercept, this one over here. So the one that's a little bit to the right, or the middle one here. So first I need to give it a left bound. So let me go a little bit to the left of that x-intercept. I think that's a little bit to the left. I'm going to hit enter. Now let me go a little bit to the right of that x-intercept. That's a little bit to the right. All right, I'm going to hit enter. And it says that the x-intercept right there is -1. So I have another x-intercept at -1, 0. And then let me find the third one. Again, second calc. I'm gonna go to 0. And let me try to find the rightmost x-intercept. So once a left bound, I gotta be a little bit to the left. Oops, I went too far. I think that's a little bit to the left of the third x-intercept. Let me go a little bit to the right of it. And let me hit enter. All right, and my calculator just computed that my x-intercept is 2. So 2, 0. So it looks like I have 3 x-intercepts, yeah? What does that mean? So these are x-intercepts. And turns out that if you know the x-intercepts of your polynomial, then you actually know the linear factors of the equation of your polynomial. So then look, what I'm going to say is the following here. I'm going to say x plus 3, x plus 1, and x minus 2. These are the linear factors. So then look, my polynomial h of x turns out, well, we know what it is. It's x cubed plus 2x to the second minus 5x minus 6. Turns out that this third degree polynomial, if if we had factored it by hand, factors like this. It factors as x plus 3, x plus 1 times x minus 2. I think that's kind of pretty neat. If you know the x-intercepts of your polynomial, or the graph of your polynomial, then you also know the linear factors. You know the factorization of your polynomial. Yeah, that's important to know. X-intercepts and linear factors sort of go hand in hand. Notice that the signs are reversed. If you have a negative x-intercept, like negative 3, 0, you have x plus 3. It becomes positive. If you have a positive x-intercept, then you have x minus 2 as your linear factor. Yeah? So let's graph this. So we said that we have negative 3 is an x-intercept, negative 1 is an x-intercept, and positive 2 is an x-intercept. And I'll do my best here to sketch the little graph. We already saw it on the calculator, but that is sort of what's going on. Yeah, this is my graph h of x. The important thing to get out of this, now I guess the question, if I was you, would be, how do I factor this third degree polynomial by hand? How do I factor this third degree polynomial by hand? And well, it definitely helps to kind of have at least a guess as to one of what the linear factors could be. That's one tool. Another tool that's maybe helpful here in order to factor by hand is long division of polynomials or synthetic division of polynomials. That might also help. But also keep in mind that x-intercepts and linear factors kind of go hand in hand. They are the same thing, yeah? All right, so let's stop. Let's pause it here for this first part. We'll continue with this section in the second part. So I'll see you in the next section. Thank you.